Welcome back to Gabversity, where facts care not about your feelings, my friends. Let's have an eclipse. It's the middle of the day. So let's have an eclipse with the sun. No! There we go, Catherine. Isn't it a beautiful day, ladies and gentlemen? It's beautiful. So you know how long it took me to prepare to make this video? I had to go inside to put some cream on my arms because the sun's been drying my skin. So I go inside, and then I forget why I went inside. So I come back out, then I realize why I went inside. So I had to go back inside, put the cream on, come back outside. Then I realized it was really hot, so I had to change, Captain Deltron, True Faith, Catherine, everyone. I had to change into some shorts. So I go back in, then I forgot where my shorts were. So then it took me ages to find some new shorts. And then when I put on the new shorts, I found my old shorts. Anyway, I come back outside, and then so it keeps going over and over. Then I finally go to sit outside, and then the guy behind me, right, in the construction zone starts hammering like crazy and talking about Genesis and Jesus, and it's just unbelievably illogical stuff that was driving me crazy. So then I had to go to the front. So I've come here, and now I forgot my battery charger. So now this lecture is going to be short because I think the battery is going to die. So there you go. It took me about, I think, 45 minutes to come out here and prepare this lecture. All right, so what are we talking about today? I found this question in Introduction Peri Pilo to Quantum Mechanics by Griffith, and this is a pretty cool textbook because it is free on the internet. If you just type in Introduction to Quantum Mechanics Griffith, space Griffith, or Pearson, and then you type in PDF, you can get older editions, I believe, PDF downloads. So here is a question. Consider the Earth-Sun system, Kevro, as a gravitational analog to the hydrogen atom. So I thought this way it'd be good to run through the basic maths of things that are similar between the Earth and Sun rotation system and the hydrogen atom. Now someone's working on something I don't understand. All right, so let's do this. So first we're going to look at the gravitational potential. All right, and the gravitational potential, it's good because gravitational potential, banter is fun, Kevro, everyone else, is analogous to the electromagnetic force, which is what you would expect is part of what's binding the electron and the neutron in their apparent orbit at the quantum level. All right, so what I've done is we look at this equation. First, we want to look at the potential. V, potential energy, equals negative G. All right, now G is the gravitational constant in this universe. And that's actually a particular number, and it was created somewhere at the time of the creation of the universe. And it has not changed. Okay? Equals mass, little mass by big mass, so mass of the Earth, mass of the Sun, over the radius, which would be the radius. So if that's the Sun here, and that's the Earth, right, and the Earth is orbiting, okay, then the radius would be the distance around. Physics class in high school. Hey, bring back some memories, my friend. All right, and we made it negative because potential works negatively to kinetic energy. So hold on, now the wind is blowing my papers. Another problem I did not foresee. Okay, so remember that G is the gravitational constant, right? So G equals, gabsmacked, equals 6.673 by 10 to the minus 11, and the units are in this. It is cubic meters by kilograms by second minus 2. Now there's a reason for that. Blow my whistle, baby. That was pretty fun. Whistle, baby. All right, so this is the constant everywhere in the universe that we know of thus far. And the units are quite interesting. It's cubic meters per kilogram. All right, so that would, how many cubic meters for every kilogram? That makes sense because, of course, around the universe, right, kilograms weigh differently, right, in different places. So you don't need as much of volume to get a kilogram. And it's per second, and that's to cancel out the acceleration factor, and that will give you a constant because, you know, gravity is a force, so that means it's related to acceleration. So we cancel out the acceleration and we're left with a constant. It's quite interesting that Queen of Avocado, hello. Alrighty, so the Bohr radius. Now, let's talk about the Bohr radius, B-O-H-R. The Bohr radius, g'day. The Bohr radius is the radius that the electron orbits the hydrogen atom in its ground state. So in other words, if you don't excite it, hey, if it doesn't get tickled or excited, then it orbits without any extra energy input. So it's just orbiting normally. And what's interesting is that that state is so low that the energy emitted is actually light that we can't see. And that's why hydrogen for humans is invisible. You see? So it's not that hydrogen is invisible, it's that we're blind to the light that it emits. And I'm pretty sure it emits, I think it's ultraviolet light. I'm pretty sure. I think it's ultraviolet, yeah. And then if you excite it too much, it turns into infrared. So, and then in between, it's like visible for, it goes to the visible spectrum, then it turns into infrared. I think, don't quote me on that. You might have to fact check me. I'm pretty sure that's what it is. All right. And we have another little van. Sounds like a mini diesel engine. Can't tell. Yes, that's a diesel. As soon as they took their foot off the accelerator, you can hear the stuttering of the diesel. You think I'm correct? Oh, thank you very much. If Rob Collins says I am, then my friends, I am. So, the Bohr radius, I'm going to show you the equation for that. We did this last time, right, with actual quantum numbers. All right, so A naught, which is the Bohr radius, that's what we call it, it's A naught, equals Planck's constant reduced squared, which is the slither of the pixel of this universe squared, over G, which is big G, the gravitational constant, by M squared, by, which is the little mass, probably the Earth's mass, by big M, mass of the sun. All right, now obviously this is going to give us a ridiculous number because we're not talking quantum levels and we're not talking hydrogen atoms either. And the number, of course, happens to equal 2, from what I prepared earlier, 349 by 10 to the minus 138 meters. Now that's obviously insane. Okay, I don't even know if that number exists actually in this universe. So obviously that makes no sense. Why are we doing this? Well, we're doing this, even though it makes more sense, it gives you an idea of how we look at the hydrogen atom and the electron orbiting the hydrogen atom. That's what's important. Okay, and what's interesting is that that's one small radius. All right, so now what we're going to do, we're now going to get the energy. Okay, I'll show you. You ready? So the energy states, okay, so En means energy at whatever level. Okay, it could be energy first level, second, third, fourth, fifth. It's the general equation, equals minus, okay, mass over 2 by h squared, reduced h squared, pixel size of the universe, okay, multiplied by the gravitational constant, little mass, which is mass of the Earth, and then big mass, mass of the sun, squared, and then we close that, and we say 1 over n squared. All right, so that's this equation. What does that tell you? Well, that means that if you have the gravitational constant and you have the mass of the Earth, we know the pixel size of the universe, we have the mass of the sun. If we have all of that, then we can know the energy based upon the energy level. So what does that mean? If the energy level is 1, then this equation turns into 1, so it's just that. If it's 2, then that becomes 1 over 4. So, and it becomes a quarter of this. Okay, so what that means is that for each energy level going outwards, okay, so to get the energy level required to push the orbit to the next orbit outwards goes down by 1 over that level squared. Okay, so that means if you want to go to level 2, it's a quarter of the energy of the first one. If you want to go to level 3, it's a ninth, because 3 squared is 9, so it's 1/9 of the energy required, and it keeps going down and down and down and down, obviously, and it's going down by a factor of that number squared. All right, so you know, if you want, for example, the 20th level, then that will be the original energy by 1 over 1,048,576. I think you need to expand on your explanation of H. Yes, forgive me. H, my friends, is the pixel size of the universe. That is the easiest way to explain to people. Now, h over h reduced to h, which is what we use, is the slither of the pixel, right? So in other words, it's a pixel divided by 360 degrees to get 1 degree, but we use radians, which is another version of degree, which is more accurate. Fingers crossed that helps. I won't talk about the units yet, but I will actually. I will coming up. Okay, so let us go. So gravitational potential. Let's do it, babies. Gravitational potential equals negative. Viewers might not. They may not. I have a feeling Rob could do a better job of explaining it. G m, so gravitational constant, by mass, small mass, which is mass of the Earth, by big mass, which is mass of the Sun, over r naught, which is the radius of the Earth in its current state, in its relaxed state, we can call it if you like. Okay, now remember, now we want the kinetic energy. Why is that important? We want the kinetic energy as well, because if you guys remember when we threw a rock off a cliff, just before you drop the rock, it's got maximum potential energy. Just before it hits the ground, it's got 0 potential energy and maximum kinetic energy. So all of the potential at the top gets converted into kinetic at the bottom. Sort of like your model student, you know, they have all the potential when they're a student. Then once they reach middle age, or you know, they've finished their life, they've reached their potential. So that would be what actually happened, what came out of that potential. So the system is the potential plus the kinetic. All right, and so to get the kinetic now, because we want the energy of the whole system, because what we're finding out, right, we're comparing the Earth and Sun, we're comparing that to the hydrogen atom. So what we can find out from this equation, we can find out, for example, how long it takes the Earth to orbit the Sun. We can find out how much energy you would need to push the Earth out to the next orbital level, right, away from the Sun. So that's what we have to do with electrons, obviously, which of course is actually more important. All right, so let's do this. Now we get the kinetic energy, and kinetic energy equals, right, m v squared over r naught, which equals gravitational constant by small m, by big M, small m mass of Earth, big M mass of the Sun, over r squared naught. So that is here the orbit. So that's the Sun, and this is the Earth, and that's the Earth orbit. That's r, the radius, and that's called r naught, which is the relaxed state. So wherever the Earth is at the moment, we just call that the relaxed state. James Joseph. And this squared is what we have here. Yeah, bring it on. And of course that can simplify, because what we can do is we can put that r naught over here and just make the equation easier just using algebra. So half mv squared. Hey, Mr. James Joseph, what's going on in the world of politics, my friend? Equals gravitational constant by mass of Earth by mass of Sun over r naught. So there you go. That's kinetic energy, and there it is. Quite interesting shite. So now I will take a break to remind you guys, Speaking Human, Retarded Genius, exlibris.com. All right, let's move on to the next page. What's interesting now is we say that the energy. Can I ask you a quick question? Of course, you can ask as many as you like, my friend. Okay. Energy is the kinetic plus the potential. Right? I'm just waiting for James Joseph's question, and then when it pops up, I will answer it. All right, so we worked out that it has to be... Where am I? Right here. Do you believe in planets and space? Good question. I don't work on belief. So I work on confidence intervals and confidence levels like science normally works, which is, I'll give you an example. I am, say, 90% sure that I'm talking to a real person called James Joseph. And it's based upon lots of evidence, our interactions, your scopes that I watch. But I can never be 100% sure. The only people who are 100% sure, right, are religionists in that sense, right? So if someone says, I'm 100% sure I'm talking to James Joseph, right, the difference in the 90% and 100% is your faith. I don't have that faith. So I can never say anything is 100%. That's how the scientist works. All right, so now we want the total energy of the system, right? Okay, which is V gravity plus the kinetic energy, half m v squared. Okay, and that happens to equal, makes sense, thanks Gab, you are more than welcome, my friend, anytime. Ask as many questions as you like. Minus G M M over 2r0. So what's this? Well, that's the mass of the Earth, that's the mass of the Sun. This is the gravitational constant given to us either by God or by the creation of the universe, whichever you prefer to believe, that's fine. And 2r0, which is the radius. r0 is the radius between the Sun and the Earth. There it is. Which is pretty damn awesome. So that means, right? That means that when we combine that with the one more question, who you think made the pyramids? Comes back again to the same thing. We underestimate how intelligent we can be as humans when we work together and use a lot of slaves and have a pharaoh. There's no evidence for anything else. But you can take out anecdotal stuff and say, how did this happen? Well, then this must have been an alien thing. Well, I wouldn't say it must have, but it could be. I don't rule that stuff out. But, you know, with great claims, great evidence is required. So that's normally how I work. I am the doubting Thomas. All right. So once I simplify all of these together, what I get is I get that n squared. Sorry, Gab. Don't be sorry. Don't be sorry for anything, my friend. Which pyramids? There are different eras of pyramids. This is very true as well. You are always welcome, my friend. Anytime. I like these chats. What would be good if we have a chat invoked at the limits of knowledge? Oh, yeah. Now we're getting a good conversation. Old pyramids are built to a higher standard. That, I believe, is also true, yeah. And that's me saying belief upon consideration. That's another problem with the English language. In other languages, like, for example, in Semitic languages, belief has two different meanings. There are two different words for belief. So, for example, Arabic, which is the one I know best, you have amen. Amen is to believe based on faith, and a'taqad, which is belief based upon consideration of facts. So they're two completely different words for belief. In English, they get conflated. So when I say I believe you are correct, that's different to I believe there is no God or there is a God or whatever. But yeah, that's a really good, man. We should have like a round table of discussion. James Joseph, all of us together, just, you know, pretty cool. All right, so n squared equals G M squared M multiplied by R0 over the pixel size squared. All right, so let's come back to this. Now, Rob Collins could probably do a better job of explaining this. My version is that this is the sliver of the pixel of the universe that makes us up. Nothing can be smaller than this in our universe. This is the building blocks. And this is the mass of the Earth squared. That is the constant given to us by our limits of knowledge, aka God. And this is the mass of the Sun, and this is R0, which is the distance between the Sun and the Earth, which I showed you right up here. Sun and the Earth, R0. There you go. And that gives us n squared. So what's interesting is that if I make the third energy level, this radius is going to go through the roof. I don't know if anyone can see this relationship here, but just ignore this part for a sec. If you keep all of this fixed, okay, which it is, if it's just the Earth and the Sun, then these become fixed and these are fixed already. Which means if you increase the energy level of the Earth, the radius has to go up by a squared factor. Okay, that's pretty crazy. That means that if you want to go up to the third energy level, the radius is going to go out 9 times as big. And if you want to go up to fourth energy level, it's going to go out 16 times as big, right? So each energy level is way, way further out than the one before it. It's not a linear movement upwards, which is just crazy. So it means that you could get an electron theoretically, like, and this is just mathematically, not without the constraints of physics, but you could get it out to infinity, right? You could excite the particle to infinity. So it's not even orbiting the nucleus of the hydrogen atom, but mathematically it still is. It's just orbiting it at infinity. And that actually, it's possible that that can happen, because infinity, all you have to do is remove time. If you remove time, then infinity becomes an instant. And in fact, Roger Penrose talks about that in how the universe keeps expanding into infinity and then starting again. And that's because light does not experience time, because it does not have mass. And time is only experienced by things with mass, because there's a discrepancy between the transfer into the fourth dimension with something with mass, and so it suffers entropy. This does not happen with stuff that travels at the rate of causality itself. Very interesting stuff. I love that stuff. Anyway, so here we go. So what we've done is this equation here, okay? This equation, we know what R0 is of Earth. So experimentally, it's mind-boggling, yeah. Experimentally, we know this, and we know the mass of the Sun, we know the mass of the Earth. Like, we know them, when I say no, like to a 95% confidence level, right? And so if we plug all of these in, right, to get n, which is the quantum number, right? The quantum number of Earth is going to equal 2.574 times 10 to the 74. All right, so that just means, right, that you got to put 1, 2, 3, and then another 71 zeros, and that will be the number of the Earth, which is insane, right? That would never happen on the quantum level. Okay, and then, right, if we want to know the energy released by a transition to the next lower level, okay, we want to know one energy level to the next, okay, and the energy that is transferred is going to equal, right, 2.1 by 10 to the minus 41 joules. All right, so that's obviously almost nothing, and the reason for that is because to move it to the next level, right, we're moving it pixel size wise. So to push the Earth 1 pixel size to the next level, right, which is the pixel size of everything that makes us up in this universe, right, the Earth is so big, so you don't have to move it very far, and so the energy is going to be 2.1 by 10 to the minus 41 joules. That is so small. That is, put 41 zeros in front of the number 2021, right? 40 zeros, sorry, 40 zeros in front of the number 21. So it is so small that, what is that? Like, you would need, that is like, let me work it out. That's 3 nines, 4 nines. It is a billion. It's 10,000 times a billion, right? You would need that many just to heat up your, glass of water like 1 degree or something, right? Like those numbers are way off, but it doesn't matter because they're so small. It tells you how small it is, right? Which is insane. Okay, now where are we here? Now we want the frequency. Okay, the frequency of the photon, right? Therefore, let's work. Do you think time is irrelevant in the dimensions beyond those we can see? I would say time is relevant, but we experience time in a very illusionary form because we think we're 3-dimensional when actually we're 4-dimensional beings. And so we are interacting with the 4th dimension 4-dimensionally. So therefore there is no time. So it's like when you I mean, and you probably know this anyway, but when you read a book, right? your future you is reading the end of the book. Your present you is reading the current part of the book, right? So you're actually reading the book four-dimensionally all at the same time. You see, because you in 4 dimensions is reading the whole book at once. There's no such thing as time. But we think of it as time because we're traveling, our consciousness is traveling through our four-dimensional body. Until that 4-dimensional body doesn't no longer exist, which is interesting. And that's why the universe, anyway, I won't even get into that at the moment, but I guess that sort of half answers your question. All right, so what's interesting is that we figured out that lambda, which is the wavelength of the photon, time exists through 3-dimensional perception. That's exactly right. Well, mathematically, that we know that now anyway. Because, for example, a black hole is a 4D object which bends the 4th dimension in on itself. So the future is always towards the center of the black hole. So, for example, equals the speed of light over v. And this happens to approximately equal 1.1 light years. Now, what's interesting about that? What is interesting about this? The wavelength is 1.1 light years. Why is that important? Well, it just happens to be that we orbit the sun in about 1 and a bit years. Is that why Trump trumps? Who knows? It could happen. Yeah. So, yeah, well, obviously the Earth orbits the sun in approximately 1 year. What are the other detentions? I think you mean dimensions past the 4th dimension. Well, there are sub-dimensions, and there are sub-sub-dimensions, and then there are different dimensions of infinity, and mathematics shows us all of these, but we can't see them. There are mathematically we can see an infinite amount of timelines that run parallel to our universe as well. So there's a lot of things that we can see, and people say the maths could be wrong. Could be, but it's so unbelievably exact in predicting everything thus far. Predicted pulsars, black holes, neutrons, neutrinos. Like it predicted, you know, the bending of light through gravitational waves. Suggest string theory. Yeah, I've heard that before. I would suggest M theory, not string theory. String theory suggested 10 dimensions, and M theory has now basically superseded string theory, which gives 11. Yeah, but mathematically there's an infinite amount of dimensions. In fact, there's something called a metric space, which I'm going to talk to you guys about later once I finish my degree in a month. A thing called a metric space basically defines our existence, and each universe is governed by a different metric space. And there are some metric spaces that are mathematically constructed where every single point is one distance from another point. Like an infinite amount of points are all one distance from every other point. Now, how does that work? Try wrap your head around that one. It's a very interesting concept. All right, so that's it. We're done. We have solved the problem, and it goes to show you that is sort of, it's an analogy on how the electron works in the hydrogen atom. What's interesting about the hydrogen atom is that mathematically you can see where it's going to go, what's going to happen with excitation of particles, when you excite it, how much energy you need, what light gets emitted, all of that you can figure out. But when you go up to different, more complicated atoms, can't do it at the tip of our noses. Well, you know, it's interesting. I was talking about this in our last lecture. The Big Bang was not a point. It was a 2-dimensional point because we're in a 4D universe. So it was actually like a sheet. We have to imagine it more like a sheet, and the explosion happened all around the sheet. It's very similar to that of an atom. It's analogous, I would say. I wouldn't say similar but yes, I get your point, yeah. Because electrons actually don't orbit the nucleus. Our human brains tell us they do, but they actually don't. Or level, the closer or more relating it is, meaning, yeah. Yeah, that would be pretty true. Mathematically, I'll show you. Gab, you're smart. I wish I had your knowledge. Wow. Thanks, man. I wish I had my knowledge sometimes. Sometimes I don't have it. I'll show you, like, for example, here is a 3D construct invented by the Chinese and then by the Europeans independently 700 years later, right? So here is X x1, x2, x3, and then y1, y2, y3, z1, z2, z3. Right, so you could, this here is like a 3D mathematical construct. Yeah, that's true. This is true. If you look up group theory, actually, if anyone wants to ever look up group theory, you'll have a good time. So if we want the what am I doing here? Yeah, so you could call this a three-dimensional matrix, right? So it's a 3 by 3 matrix. So here's this 3 times 3 matrix. All right, so this is a point in space, another point in space, another point in space, right? And that's another point, another point. So if I was going to draw this in 3 dimensions, I would draw it like this. Okay, so here is my 3 dimensions, right? And x1 might be here, y1 might be up here, and z1 might be here. And then what I got here is other points, right? So, and then that becomes, what have I done here? That's supposed to be a really bad drawing of a cube. All right, so this here is a cube, right? So you got 1, 2, 3, 4, 5, 6. 6. What have I done? 1, 2, 3, 4. Yeah. 5, 6, 7, 8. I've done something wrong here. What have I done wrong? It should be 9 points. Why am I getting 8 points? Oh yeah, no, 8 points because 2 cubed. Yeah, so it should be 8 points, right? Now, if you want to draw a 4-dimensional object, that's going to become very difficult. What you're going to have to do is you're going to have to say 4D object, right, which equals omega, right? You could say equals x1 plus y1 plus z1 plus k1, right? So here now is your 4-dimensional object, right? And you would call that omega, okay? So what happens is, if you want the area of this, you can still get it, but what you do is you use this matrix and you get something called a determinant. The shadow of 4D is 3D. That's exactly right. In fact, I have some of them here. Here are some 3D quantum mechanic waves. Right here. So this is a 4-dimensional wave, but our human brains can't see it. Hello, Beretta. Because our human brains can't see it, then we slice it up into its 3D versions. So each one of these is a hydrogen atom in a different energy state, and the atom is represented by 3-dimensional waves. So that's where you would likely find the atom itself, the particle, sorry. Okay, and as you give it different energy states, right? So these are all snapshots in time, instant snapshots, okay? But if you think about it, in real life, if you wanted to look around this particle, you would need time to do it. And so by the time you get to the back, this will have changed shape to this, for example. So if you were looking around the particle, you wouldn't see that particle. You would see, at the front, you'd see one, and then at the back, because time has passed, your future self is now seeing a different part of the 4D shape, and your brain will put it together and you get a weird shape in your head, right? So that's very, very interesting. Quantum mechanics came in college many years ago, but wasn't an electrical engineer by. Oh, cool. Yeah, well, that's not an easy task, my friend, so well done. Anyway, that concludes our lecture today. What's my next one going to be? The next one I'm going to do for you guys will probably be a lot more mathematics involved. No, we're going to do angular momentum. So there's going to be no maths involved. It's just going to be concepts. We'll talk about angular momentum in quantum mechanics. Control systems. Oh yeah, absolutely. The future influences the present all the time, but our human brains confuse it as being the past. Because we remember things that we think happened in the past, and then we define it as the past. So it's defined as the past because of how we remember it. That's why time itself is an illusion, right? There is a law of entropy which creates a pattern. And that pattern looks like we're traveling into a future, but that's not really what's going on. For example, here in Australia, mental illusions, yeah, absolutely. It's all one big four-dimensional object. Yeah, they all coexist, yeah. They're all like one big chain that all is connected. So I'll give you an example. In Sydney, I'm in Sydney, right? So at the moment, the waves of the ocean are running westwards and hitting us at the shore. But you guys, let's say if anyone's here is on the California side, on the Pacific side of the US, right? Then your waves are actually going the opposite way and are hitting you guys from the west towards the east, right? So you can imagine time as something like that in different parts of existence. Time flows one way where it flows another way somewhere else, okay? And that's only because the collapse of order into disorder is happening in a certain direction, and that's the direction that we follow, because we are made up of that stuff. We're made up of stuff that's decaying. And so the rearrangement of particles allows us to remember things that happened in one direction. Anyway, next one will be angular momentum. I will probably go have a tea or something, and then I'll come back and talk about angular momentum. Gavversity, where facts don't care about your feelings. And once again, xlibris.com, $5, go download it now. Speaking Human, the tragedy of my life in the Middle East and Australia, in the wars, being arrested, being abused at school, the bullying, the violence, growing up with autism, then discovering I was some sort of genius. It's all there, my friends. And you can go to YouTube at Gabsmacked and then listen to some of the book readings, and you might find that you want a copy of that book. All right, all the best. Mwah. Gabsmacked, where facts don't care about your feelings.